Hi everyone, welcome back to the Applied Thermodynamics session. So before we really go to each of the chapters, I would really like to share and refresh you guys about some basic engineering thermal equations, and also two of the conditions that's very common that we use in our the further chapters. So when we look back into your engineering thermal, very common we deal with perfect gas because we want to know the perfect condition, what happened, and then you are going to involve more complicated condition. So if you look at this slide, so I apologize about this quality because I can't get my scanner. So at least we can see this together. Yeah. So, okay, back to this. So our perfect gas law, right, is, our perfect gas law is PV equals to RT. The V is specific volume. So if you want to be, what does that means is you are per mass. So if you want to change it to PV, the volume, so you have to replace it over the, you have to replace it with this equation 2. I think that is quite simple for you. So specific heat capacity, we have two. One is CV and another one is CP. CV is constant volume. So if you refer to your Chankel, CV is normally often the internal energy is related to the CV over the delta T. You can write it as the heat is the Q, delta Q equals to mCV delta T at constant volume condition. For CP, it means constant pressure, so it's normally deal with enthalpy delta H over delta T. So if your condition is at constant pressure, your delta Q can be write as mCp delta T. Okay, so let's go to the Joule's law. Joule's law is very easy. Heat plus work. If your work done by the system is negative, so be aware on this part. If your work done on the system, then it's positive. Equals to delta U is the internal energy. So we know that the work is equals to P delta V. The pressure push the volume, the changes of the volume. But if you are in a constant volume, means this whole thing is equals to 0, right? So then your work is equals to, okay, so I repeat again, because at constant volume, these things will become 0. So your work equals to 0. So it's equals to delta Q equals to delta U. So since we have equation 3, delta U also equals to CV delta T. So therefore we have this equation here. Okay? So go back to the, let's say, what is the relationship between the CV and the CP? For perfect gas, okay, delta U equals to CV delta T. We can move around, so we can have CV equals to du over T, which is same like equation number 3. So at constant volume, as constant pressure, the work equals to P delta V. So at this point, the delta V is keep on changing, correct? So what is that means is we have V2 minus V1, right? So now we put the equation 2a PV equals to MRT into, we put this into this equation. So we can have W equals to M, we replace the P equals to MR, okay, the MRT. So the T is changing, right? So we have equation 6 here. And back to the Joule's law, Q plus W equals to U. But in this part is the work done. Therefore, your W is negative. So Q minus, we put this equation inside here, MRT, okay, equals to, the U is, we can use, because U is CV delta T, we can use, since this is have an M, we have the M, CV T2 minus T1. So you can move this to this part, then you can get equation 7. And we also know that the Cp equals to delta H over delta T. So we can have the Q equals to mCp T2 minus T1. So this is equation 4a that we learned from this part. Can we change to blue? Okay, so we put 7 and we put 4a into the Joule's law. Okay, so we have the Q, we put in the Q, this is the Q, this is the equation 7, so just plug everything here, and we try to simplify it, because this one we have T2 minus T1, cut it, we have the same mass, we cut it, so Cp minus, because then we have Cp equals to Cv plus R, and we can move the Cv to the Cp side, so equals to Cp minus Cv equals to R. So from equation 8, we know that, too fast. So Cp definitely much larger than Cv, agree? So, and then we look at the specific enthalpy of a perfect gas. I'm sure you learned this basic equation in engineering Thermo. Your specific enthalpy equation is H equals to U plus PV. The V here is specific volume, not volume. So we know that the PV equals to RT. We also know that the U equals to CVT. So we put these two equations inside here, right? And then you can have this equation. So the H equals to CV plus R times T. And then we put the equation 8. It look very similar, isn't it? If I put the CV back to, in equation number 8, if I put the CV go to this side, right? I have Cp equals to R plus Cv. So means I can replace this to Cp. In other words means H equals to Cpt, or H equals to mCpt. In this part is the T is the temperature. Why I want to explain this all to you, some of you, no, quite a lot of you mentioned that you are confused about the equation, you don't understand the equation. Rather than you memorize the equation, so I think it's easier for you to understand the basic first, and then you go to a bit advanced. Okay, the next is the ratio of the specific heat capacity. All this information are very useful for the next few chapter in this applied thermal. So please put attention on it. I won't give you any equation, if possible, during your test. So you should able to understand and have a quick work out on it and get the equation if you don't have. So ratio of a specific heat capacity. So Let's make the gamma, is Cp over Cv. So from equation 8, where is the equation 8? From equation 8, we know that Cp definitely bigger than Cv, right? So in other words means this ratio should be more than 1. Okay, so we play around with the equation 8. We try to divide by Cv. We have Cp over Cv minus 1 equals to R over Cv. And then we play around with the position. We can have the equation 11, which is Cv equals to R over gamma minus 1. Okay, so again, although we are in advance, we're still learning about perfect condition. So we often deal with the reversible and mostly reversible. So for the reversible non-flow process, constant at constant volume process, okay? So let's back to the Joule's law. So Q plus W equals to U2 minus U1. We know that the work is P delta V equals to 0. So, but it's constant volume. You're not moving the volume. So therefore your work is 0 and Q equals to U2 minus U1. And since you know CV equals to du over T, so we in this case we can say at constant volume Q equals to CV delta T and the work done is 0. Okay? So for the constant pressure, we are still moving the volume, okay? So we have negative because it's work done by the system. So P, volume 2 minus volume 1. So again, back to the Joule's law, Q plus W equals to U. Because the W is work done, is negative. It's done by the system, so it's negative. So we put in everything in there, and we can rearrange this equation into U2 plus PV2 minus U1 plus PV1. And this arrangement quite similar with the specific enthalpy equation, isn't it? So therefore, we can replace this as Q equals to H2 minus H1. That is very good. Means we can refer to the table, the thermodynamic table, just for example, the certain pressure, and then you can enter temperature, and then you can get your H1, H2 minus H1, and you can solve the problem. So let's move to further a bit complicated. Maybe you learned this before, I'm not sure, but this is definitely useful for the next few chapters. Isothermal, like I mentioned to you, thermal is heat. When we deal with heat, we know we are dealing with temperature. Iso is same, constant. So isothermal means constant temperature. So if you draw the PV diagram, this is the PV diagram for constant temperature. So the PV equals to constant. So the work equals to negative P delta V. Okay, so if you refer to this equation, we can replace the P equals to C over V. And if we do the integration, this is what our work done. But you say, hey, doctor, you just mentioned delta V equals to 0. Why you want to play so much things? Because we want to find more other way to solve the isothermal condition. So be patient, yeah? So let's say, so C is constant, yeah? So since this C is constant, I will say P1, C equals to P1 V1 or C equals to P2 V2. In other words, means P1 V1 equals to P2 V2. Sounds familiar? Now you understand? And we, from this equation, the W equals to C ln V1 over V2, we've replaced this into the C. So we can have equation 13 or equation 14. Hey, we still can play around with, since P1 V1 equals to P2 V2, we can rearrange it and replace the V1 over V2 to using this equation 15. And therefore, you can have equation 16. Or, yeah, you can have equation 16. Or you can have W equals to P2 V2 ln, what? V1 over V2, P2 over P1. Yeah, you can use this equation to replace in equation 14 or equation 13. Okay? So, then we also know that P1 V1 equals to RT. So we can replace, if you don't have, you only given the temperature, you don't know the pressure. That is quite, I don't know, quite impossible. Yeah, for example, you don't have the volume. It's happened you have the pressure and the P2 and the P1 and the temperature given. So in this case, you can use this equation to solve it. Yeah. So back to the Joule's law. Because this is isothermal, so the temperature is equals to 0 and our delta U internal energy is equals to 0 for isothermal. Okay? What about adiabatic non-flow process? So adiabatic, we know that Q equals to 0, no heat in and no heat out. No. Okay, so means that our Q is 0. So our work equals to U2 minus U1. And we can still play around with it. We try to play with, change it to delta Q plus delta W equals to delta U. And we put this equation into delta W. Okay? And therefore, you have this equation, equation 18. And we refer back to our specific enthalpy equation, which is H enthalpy equals to internal energy plus PV. When we do the differential equation, so we can have differentiated delta H du plus P dV plus V dP. Okay, so we rearrange this one to more similar to specific enthalpy equation. So we have du plus P dV, dH minus V dP. And then we refer back to this equation. Okay, P dV plus du equals to 0. Equation 18 say P dV plus du equals to 0. In other words means this equation is 0 equals to delta H minus V dP. Agree? Yes? So we back to equation 18 again. The equation say du equals to dq equals to du plus p dv equals to 0. Agree? And I still can play around with it because this p, I can play around with the perfect gas equation. And then my du, I can change it to cv delta t. Okay? And I try to divide to t. I remove the t to this side. And this one, look, quite okay. We can do something with it. So let's do the integration this now. So when we do the integration, Hold on. Okay. Yeah. So when I do the integration of equation 20, I can have CV ln t plus r ln v equals to constant. So I also can put the PV equals to RT to replace the T. I can put this inside here. So then I have ln PV over R plus R CV ln V equals to constant. So from equation 11, our equation 11 is CV equals to gamma minus 1. So we can play around and put it here. And therefore we have ln PV over R plus gamma minus 1 ln V equals 0. So why I explain this? Sometimes, most of the times, gamma is given and happen that you have the pressure and the volume and you can solve the whole thing. Okay. Or just now we can use this equation. Okay, I can put this up. Then I have, oh sorry, too fast. So then I have ln PV over R plus ln V power of gamma minus 1 equals to constant. Then I sort this out, and then I try to move the ln to this side. Okay, since this is a constant, this is C, and the R also constant, I put it here, and therefore for adiabatic, P1 V1 lambda equals to P2 V2 lambda. Is that okay? So you have to remember these things. Probably you might think it's quite complicated, but once you go to further chapter, you might find this very useful. I will try to get a proper scanner for myself, and then I will make it better for the resolution. At least now you can write it down and try to understand it first. Is it okay? So thank you everyone. I will send another lecture notes on Monday. It's about internal combustion engine. So yeah, stay tuned. Take care everyone.